I know what I gotta do here. So I just want to get a good camera angle since we're gonna be drawing for a while. Okay. So I further designed, after looking at some more photos and thinking about it closer, the combustion cylinders. Basically, we're gonna have, let's see. Servo or Meredith. This is the piston. And oh great. I already screwed up. Alright, let me just draw it quickly. I think I'm trying to draw it too neat. Let me just draw how I draw, whatever. Alright, so we got that. And like that. And then these are spring loaded, I believe. And then this is gonna come up. Then right here will be the spark plug. And then alright. And there you have it. Then you've got, so this is the cylinder and the piston. The piston is going to get exploded that way. And then you've got an exhaust pipe here. It's going to come like that. And then you've got your okay. Fuel in, exhaust out. I believe it's gonna be like around 4 inches long, and yeah, I mean that's a pretty simple design. Hello, woman from Norway. Okay. I am a blonde woman, half skier. Well, welcome to the stream. I tell everyone I'm from Norway, but I just made it up. Alright, so does this all make sense to you guys? These are valves. So these little trumpet valves, wait a minute, are they spring-loaded? Yeah, so that would be like that. The springs, wait. Yeah! Okay, so then the tops of these can get pulled by a motor. Little servo motor can just reel this string in, which will lift the valve that way, and the spring will open it back up. So if the motor turns counterclockwise, relaxing this string, the spring will push the valve open. When the servo motor turns clockwise, it draws the valve back shut. So that's how you can control opening and shutting, using a spring for the opening and the motor reeling the string in for the shutting. And the trumpet-shaped valve is the same shape of valve used in an automobile. So basically, the valve has like a hole, and when it shuts, it closes the hole. So it will look like this when it's shut. Open. Air can still get through. Shut. No escape. So that's how the valves work. No escape. It's fully sealed and it's open. So based on that. So it's really a great design. And what's also great is when it's shut, you actually have combustion pushing hard into it, trying to rip that valve through. But since it's metal on metal, once it's shut, it's not going to blow open. So it can't squeeze in any further because the size of the valve is greater than the size of the hole, so it can't be pushed through the hole. So the force of the combustion actually just makes the valve even tighter. So that's why it's a brilliant design for a valve in a combustion chamber. Everything upstream of this piston head is the combustion chamber. So the piston head will start out up here, and this is going to fill with fuel. And so the fuel valve will be open, the exhaust valve will be shut, the fuel will enter. The fuel in our case is most likely going to be hairspray. The fuel will enter in the fuel in hose because the valve will be open. And then, and by the way, this valve actually just enters in the side of the hose. It's kind of hard to see that, but it just enters in. So the hose encapsulates the valve. So the valve is inside the hose. So anyways, the valve opens up, the fuel sprays in under pressure and fills this chamber with fuel. Then this spark plug right here sends out a spark, causing the fuel to ignite. Obviously this fuel inline will be shut before that happens. So this thing shuts, the spark plug ignites, causing an expansion of the gas from combustion, forcing the cylinder or the piston down into the cylinder. It's going to have a 4-inch stroke because that's about the amount of stroke I'll need to cause 2/3 of a muscle contraction. So like if this cylinder were aiding the bicep muscle, 4 inches of stroke means 4 inches of string connected from here to here pulling the arm up. So I think about 4 inches of stroke should be about a good amount. Might even be less. Just depends on how far down your attachment point is of the muscle. You attach the bicep here, and then you attach it somewhere in the forearm. And then the amount of stroke is just is determined by how far down the forearm you attach it or how close to the joint you attach it. So if you attach it really close to the elbow, it will travel less distance but cause the arm to move more. So you can control your speed and power, basically down gearing, based upon how far or how close to the joint you attach the muscle attachment. So 4-inch stroke, and then I don't know what the bore will be. In other words, I don't know what the diameter of the cylinder will be. So that probably will require experimentation. I believe the larger the diameter of a combustion cylinder, the more fuel you can put in, the greater the size of the explosion and the more power it will have. So if I only made this a 1-inch diameter tube or a 1/2-inch diameter tube, it would be a lot less weak than if I made it like a 3-inch diameter tube. The way I drew it, it looks like it's about, if this is 4 inches tall, it's about 3/4 of an inch in diameter according to this drawing. But I might make it really a lot greater in diameter if it turns out I need more power. Okay, so anyways, the spark plug ignites, driving the cylinder down. And the air, the expansion of gases is what forces it down. And both of these valves are shut, so the air has no place to go. Now, once the cylinder reaches the bottom, we don't want it to go through the bottom like a bullet, so we need an emergency air release valve, which I'll put in for the drawing. So here's the exhaust out pipe. I'm going to extend it further. Okay. We're going to put our emergency air relief availability down here. This is another exhaust pipe. And then we'll just pipe that into this exhaust. Okay. So it's just going to rejoin with the other exhaust lines. And what's going to happen is once this piston head reaches the bottom, all this explosive gas, having no place to go at this point, can now come out here and stop pushing the head down, because we don't want the piston head to break through the bottom of the chamber. Okay, you're describing nearly a two-stroke engine, but where water will be evacuated. Well, there's not going to be water. This is all air. So air, the fuel enters, the fuel ignites and turns into a gas. The gas expands, driving down the piston. And then the gas needs a place to escape after the piston has been drawn to the very bottom, and it's going to escape through here, through this exhaust vent line here. So that will enable those gases to escape without the piston head going down too far. We don't want it to keep going. So the piston head, because it's pulling a load, it will get slowed down as soon as the gas has a place to go, so it's not going to keep going downward. Even though it will have momentum, there's going to be a load that it's going to be pulling, so it's not just going to fly and smash into the bottom of the cylinder with a lot of force breaking it, I don't think. Especially if it's all metal construction. Now, after it hits the bottom, the servos controlling the arm that this is just helping out, or whatever muscle group this is just helping out for the extra burst power, will allow the arm to open back up, and when that happens, it's going to reset, so it's going to draw this back up as the muscle relaxes. So this helped the muscle to contract. As the muscle relaxes, it will draw this piston head back to the top, basically resetting it. Now when that happens, you have no place for the air to go, and so when the muscle's ready to relax, this servo motor right up here will turn counterclockwise, releasing this valve, and the spring will push the valve open, thereby opening the top exhaust exit. And so all this air, which has nowhere to go, now has a place to go. So because otherwise, if you tried to pull this piston upward with all this air trapped in here, the piston would not be able to go upward without compressing a bunch of air, so it'd have a lot of resistance. So you release the exhaust out valve, allowing the piston to go back up with the air having a place to go. Now, another thing which I mentioned in some of my video descriptions covering this system is our original plan was to try to cool the exhaust air, which we can still try to do, and then send it out through the anus of the robot, because we don't want to send it out through the normal exhaust through the nose, because that could melt the nose. I didn't want to send it through the normal exhaust lines, because that's where all the exhaust for the whole robot will be, and I don't want all the robot's exhaust to get overheated because of the exhaust from these combustion actuators. So what I came up with, I was like, so where can all this explosive gas leave the robot safely? And if it leaves through the anus, it could literally start his pants on fire. It's just too risky. So I thought, what other orifice of a human body could it come out of? And then that made me think of the mouth. So the robot could just open its mouth really wide and have a metal pipe coming out of his throat, or through the roof of his mouth, I was thinking, kind of angled toward the chin a little bit. And he'll be like breathing fire, basically, like a dragon. And his entire mouth can be coated in water regularly, and cotton with water, so it's going to be soaked, and so that will prevent any of the inside of the mouth from burning, because it will be cooled very quickly. Plus, all of the exhaust lines can be wrapped in cotton cloth. So it's going to be wrapped in double stick tape and then cotton cloth sewn tightly around it, and then the cotton cloth soaked with water, with our sprinkler system, which I designed for the robot, which is basically just a series of hoses with holes in them that will spray water in strategic spots throughout the robot under pressure. So water will spray, forming little puddles that will spread. and that will coat all the piping for the exhaust with cotton soaked with water, cool water. And then as air blows across that, it's going to evaporate the water, and as the water evaporates, it cools down whatever it's in contact with. So the exhaust lines will steam and cool down very quickly and make a hissing sound, and the hot situation will be taken care of immediately and vented out through the robot's normal ventilation systems. Now, for these, so this is the design. That's pretty much the final design. Okay, so I can tell you what the difference is between this and a two-stroke combustion cylinder. The only difference, this piston is flipped upside down. So the piston in a vehicle comes down the bottom, right? And then it connects to the crankshaft, and there's several of them, and it turns the crankshaft like a bike pedal. So the piston acts like a bike rider turning the bike pedal, and then the crankshaft turns, and all the pistons work together to turn this crankshaft. So basically I just inverted it to make it, instead of pushing down, it's a pulling force, and it pulls from the top like a muscle contracting. And so that's how I redesigned the combustion engine to be a combustion-based linear actuator who pulls on the load like a muscle for humanoid robotics. So that's my twist. And like I said, the power can be increased by increasing the diameter, and the draw stroke can be increased by increasing the length. The other thing I changed about a car engine is a car engine does not have a relief port here. But I put a relief port there just as a precaution. Perhaps it's not necessary. I mean, if you can time it right, once the piston reaches about near the bottom, you could just open up the exhaust out and relieve the combustion pressure that way to prevent the piston from just keeping driving until it hits the bottom and possibly breaks the whole cylinder. So that's one way you could do it. But I just think this is a lot safer, having a relief port here at the bottom of the chamber, just to make sure that the explosion doesn't just, I mean, you're trapping combustion inside a pipe. You need to make sure nothing's going to prevent that air from escaping, because if this piston hits the bottom of this chamber and you haven't yet opened, for whatever reason, the exhaust out port, once that gas fills, it's going to pressurize this container, and it's going to bend the container walls out, and it's going to cause a literal explosion. It could be like a grenade, and there's going to be metal shrapnel spraying everywhere, and that's like literally a grenade happening in my house. It could kill somebody. So it's very important to have a guarantee that that gas has a place to go. Now on the upside, it's unlikely hairspray fuel is going to be powerful enough to cause an explosion big enough to kill somebody. But I'm just talking in theory here. And plus, we might end up using gasoline. Hairspray was my first choice, but I might use gasoline. You know, any type of fuel can come through here. Maybe gasoline would be better than hairspray. Now that I'm using a proper design, exactly like an automobile, there's no reason I couldn't use gasoline. Maybe the robot could have a special, like, little port inside his mouth where he can drink gasoline and refill his gasoline that way. He could open up a valve in his mouth, in his throat, and drink the gasoline. he has another valve that he'll be able to open when he's drinking water, and another valve he'll be able to open when he's drinking ice cubes. So gasoline can be one of the many things the robot drinks in order to refuel himself. I think hairspray... Well, I don't think it'd gunk up the cylinder because the cylinder is exploding, and I think the fire would vaporize whatever gunk is in there. But it could gunk up the fuel inline, which is why I considered like tapping into that with another tube and like whatever valve leads, let's see. Well, maybe not. Wait, maybe not. If hairspray literally is filling the entire fuel inline, and this is pressurized, then the hairspray is literally inside here. Like, let's say it was filled up to here, and this is all hairspray. Well, as the hairspray lowers, it's going to leave gunk on this pipe. So yeah, once the hairspray is fully emptied, it would be smart to just send like paint thinner down here and just spray it out, and then maybe like have a drain port so that, like, you can like maybe a flushing system that just cleans out everything. That could be automated too. Just like another line that enters the fuel in, and then that will be your paint thinner. Could just be in here, and that could have its own valve, its own trumpet valve, and its own actuator. And when it opens after your hairspray is all empty, like after however many uses, it can pour the paint thinner into this tube, clearing it out. It could fill this tube with this closed. It could fill it and just let it soak for a while. And then this valve will open and drain the paint thinner into your combustion cylinder. And then you could have like, let's say if the piston were here, you could put another line with another valve, right? That is a drain line. So you can drain it out through there. Or yeah, that actually would be good. So you can clean your entire combustion chamber that way with just a bunch of paint thinner. Just soaking it and then draining it out. Don't you think you get some space issues if you want to control every muscle individually? Space issues are the whole challenge of the robot. That's the entire game. Building a humanoid robot is a space issue solving puzzle. That's the entire thing. You're trying to come up with ways to maximize the space of a human body in every way you can. But that's usually the case with any electronics design. Think of like a GoPro. I don't know if you ever watch electronics teardown videos, but like GoPros fit so much stuff in such a small package. Same with cell phones or anything else. It's when you get into advanced electronics, space solving issues is the name of the game. That's what it's all about. Do you have fast enough servo to release the exhaust? I won't have to. So, I mean, it's not so much the speed of the servo, it'd be the timing of the servo. But I don't even have to worry about it because the exhaust will release through this emergency port, exhaust release port on the bottom. And then this servo just opens for when you're ready to relax the muscle and recharge it. Basically pulling the cylinder back to the top by putting pressure on this string. You lift it right back out. And for that you need to open up the exhaust out valve in order to let the air release as you lift the cylinder back up. So the return stroke of the cylinder will be done by servos that are controlling the joint that this is connected to. So when the servos contract the opposing muscle group, let's say that this cylinder helped the bicep to flex, right? Boom. And it only needs to be 2/3 of it. The rest will be momentum after that. So it will do 2/3 of the flex when it needs a lot of power. Boom. So this thing helped the bicep to flex. Now, when the tricep muscles controlled by servos release the arm, what's going to happen? The string that got pulled to lift the bicep now is being pulled in the other way as the tricep flexes. It's being relaxed. And that will open up our combustion cylinder by pulling up on the string, drawing the cylinder back into a recocked position. So it's reloaded, ready to fill the fuel and do another explosion. Now, in the case of running, I realized that it's going to need to do that over and over. Boom, 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 boom. Every time the leg takes another stroke, it's going to need another explosion from the combustion cylinder. So this will need to reload, refuel, boom, reload, refuel, boom. Just like a car, it's going to just keep on boom, 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 over and over and over. Are you serious? How can you power a muscle or even a group of muscles in that way? I'm completely lost. So this cylinder can be mounted anywhere in the robot's body, right? So let's just draw the cylinder in a simplified way. Okay, all the cylinder does is pull on this string. And then this string can be sent through hosing and turned anywhere you want throughout the robot's body. And it's going to be able to pull. And so you can have the cylinder be inside the chest, for example, go around the shoulders, and then tie down here. So you can have, let's see, scapula, and then clavicle. Then you got your femur, no, not your femur, your humerus, and you got your ulna, and your radius, alright, so you got your robot's hand. I'm spending too much time drawing the bones. Okay. Now, you want your string to attach from here to here. Okay. And then this is strapped into the bone, and this is tied into the bone. Okay? Now, when the combustion cylinder pulls this way, it's going to pull the string all the way through, all the way through, all the way through, and end up pulling from here to here. It's going to be pulling where it's tied off, where the end of this string ends. And that's going to lift the arm this way. You get it? This is the shoulder, bicep, forearm, hand. When this combustion cylinder in the chest pulls, it's going to pull all the string, and then it's going to pull this string. It's going to draw it in. And thereby flex the bicep. So you can put this anywhere in the robot's body, and it can move anything just by setting up the hosing and the wiring. It can move any muscle. Now, I plan to probably put these in the chest. Possibly like in this area. Maybe mounted behind the lungs or below the lungs. I want the batteries to be like in the lower stomach region. Maybe these can be like in the upper stomach region. Or like the upper back. It has to be behind the lungs. So it's going to be tough finding a good place for them because they're going to generate a lot of heat and it's going to be an issue. But by wrapping these cylinders in cotton or double stick tape and then cotton cloth and soaking them in water, that should prevent them from giving off too much heat to damage any nearby electronics. But it's still going to be kind of scary working with them. I'll probably have to heat sink them really well. We'll have to figure that out. It's scary putting combustion and explosions inside a robot, but hopefully we'll be okay. So my idea is to have about 11 of these. I figure we're going to need one of these for each calf muscle. We're going to need one for each leg's hamstrings. We're going to need one for each leg's quadriceps. We're going to need one for the lower back. We're going to need one for each bicep. So I want to have explosive power for punching or pulling. So I guess we might need it for the lats as well. So the lats would help with pulling, for really pulling explosively plus the back, so it can do this. And then for punching, I guess it would be needed for the tricep. So yeah, maybe triceps, biceps. So I don't know. We might have. I'd like to settle around 10 of these. Now